we would be discussing about the application of species balance equation, which is nothing but the conservation of mass for species A, and we have seen how the conservation of species A, B, C, etc., when they are added together, it would give the continuity equation that we are familiar with. So when we see the species balance equation, there is a temporal term which denotes the variation in concentration of one species at with respect to time, and there are other terms which would talk about the convective mass transport of species A, and on the right hand side we have the diffusive transport of species A because of the existence of a concentration gradient. And the last term that we have included, that we have identified to be something which would result in a change in concentration of the species A as a function of time and position, is the generation term. So the most common generation term or depletion term that we can think of in mass transfer is through reactions. So the species balance equation is a statement of conservation, of mass. It has temporal terms, it has terms containing velocities which denote the convective transport of mass, which is due to the flow, and so on. So it would also be useful to start with a problem where we would see the increasing difficulty of expressing the species balance through a shell mass balance approach. So far the shell balance approach was very successful, but as we have seen before with the case of momentum transfer and with the case of heat transfer, the moment the geometry becomes a bit more complicated, and when we have to take into account the variation in the measurable quantity, which in this case is concentration, is a function of more than one space coordinates, or if it is a function of time as well, then expressing that in terms of an imaginary shell becomes increasingly difficult. So we would start with the problem of diffusion in a falling film. So we have a wall, and along the side of the wall a film is falling vertically. So let us say that liquid film, we denote that the liquid solvent here as B, and there is a gas present in contact with the falling film, let us say A. So A is the gas which is going to be absorbed in the liquid, which is B, and then the species of A will start its downward journey along with the film, and we would try to find out what is the concentration distribution of A in the falling film, or more importantly what is the rate of absorption of A into the falling film. And pictorially it can be represented in this way, where we have this as the solid wall. So this is the solid wall of width W and length L, and I have a liquid film which is falling. This wall is vertical, the liquid film is coming down, and there is a gas A which is going to be absorbed at the liquid gas interface, and as the A molecules get into the falling liquid, it is going to start its downward journey. But as it starts its downward journey, there exists a strong concentration gradient and on this side. So it will start its convective motion downwards, and there is going to be a diffusive motion of the species in the x direction as well. So in the z direction I have the presence of both convection, and since the concentration of A will vary depending on where we are in the z location, there could also a diffusive current, a diffusive motion of A molecules in the z direction may also be set up. So the system is then a gas being absorbed in the liquid, and the gas starts its diffusion convection motion in the falling film, and we need to find out what is the concentration profile of A in the film, and how much of A is going to get absorbed in the falling film as a function of parameters, which could be the geometric parameters like the thickness, the width of the wall, the length of the wall, the diffusivity of A in the liquid B and several other factors. So, if we start with our shell balance approach, we have always assumed the shell to be the smaller dimension of the shell was the direction in which the concentration or the temperature or the velocity is changing. But if you think of the figure that I have just described to you, the concentration is changing not only with Z, but it's also changing with Y, not only with the along the film, but across the film as well. So if I have to choose a shell, it's going to be of size delta Z, delta X, and it could be any Y, because none of the parameters would depend on Y. So coming back to the figure once again, so this is my delta Z. Since my concentration changes with Z, so this is going to be one of the smaller dimensions. It's a function of X, since we have a concentration gradient in this direction. So delta X is going to be another one. So what I would get is some sort of a rod like structure in which this is delta Z, this is delta X, and it could be any length Y. You can take that to be Y as well. And across these faces, there's going to be convection and diffusive motion. So you can see how complicated. I mean, it's coming to a point where it's easy to make a mistake in identifying what would be the mechanism by which the mass species A enters the control volume or leaves the control volume, and so on. So this is this problem has been presented in Bode-Stewart-Lightfoot using this shell species balance. So you can take a look at that. But what we are going to do, since we know what is species balance equation, in what we are going to do now is we are going to simply write the equation, the species balance equation, in rectangular coordinate, in XYZ coordinate, and in Cartesian coordinate systems, and we'll simply cancel the terms which are not relevant. So we will skip the requirement of defining a shell, identifying the mechanisms by which the species A enters into the shell, and arrive at the governing equation. So this is going to be the case. So I know that in Cartesian coordinate system, the species balance equation, which is also there in any of your textbook, is this is the one which we have discussed in the last class. So this is the concentration of species A as a function of time, and since it has velocity in it, so it's going to be the convective term. This is the diffusion coefficient. So this is the diffusive term, and we have the rate of reaction which consumes or produces A. So first of all, we are going to make certain assumptions. First off, there is no reaction. That means A does not react with B. So A and B are non-reacting to each other, and we have a steady state which is reached in this case. So we are solving the problem only at steady state. And the third one is A is slightly soluble in B, that means the mu is remaining a constant. So mu is a constant. And the fourth one is diffusion of A into B is a slow process. That what this simply tells us is that the penetration of A into the B is taking place over a period of time. It's not a very fast penetration. So the other one is it's laminar 1D flow, such that we have velocity So we have only Vz, which is not equal to 0. There is no velocity in the y direction and no velocity in the x direction. So now I am going to expand this. If I expand this, it's simply going to be del Ca del t plus Vx del Ca del x plus Vy del Ca del y plus Vz del Ca del z is equal to dAB del square Ca by del x square plus del square Ca by del z y square plus del square Ca by del z square. I am not writing the Ra term since I have already assumed that there is no reaction which is taking place. So there is no question of generation or depletion of A in the liquid gas mixture when the gas gets absorbed in the liquid. So the reaction term is dropped. This would be 0 because of 2, the assumption 2. So these are my assumptions. So because of assumption 2, it's a steady state, and this would be 0 because of my assumption 5, which says it's a one dimensional flow. So Vz is simply going to be is the only non-zero term. So this would be equal to 0. For the same logic, I am going to get the Vy to be 0 as well, since again it's laminar 1D flow. But I understand that Vz is not equal to 0 and Ca is going to be a function of z. As I move in this direction, what I am going to see is that at a fixed z, the concentration is going to change with z. It's going to increase with z since it's being absorbed by the liquid. So the entire left hand side then I am going to have is Vz del Ca del z is equal to, then I am going to think about the right hand side. So in the right hand side, what I have then is dAB will obviously be there, and del square Ca by del x square, because Ca is a function of x. So this term must be there, plus del square Ca by del z square. Ca is not a function of y because it's independent, it is independent of y. So the y dependence of Ca, this term can be cancelled, and what we have is this as the governing equation. So let's see what are the significances of each term. So this is convection in Z. This one multiplied by dAB is diffusion in x, and this multiplied by dAB is diffusion in Z. So we at this point I think we can make a judgment about which is going to be important in this case. There is substantial convection in the falling film because of the velocity, predominant velocity Vz in the z direction. So molecules of species A which are being absorbed in the liquid will travel towards the bottom at a high rate. So convection in the z direction can never be neglected. So the first term in here must remain in my governing equation. Ca as a function of x, the concentration of A at this point is probably the highest, which could be the interface solubility of A in B, and as I move in this direction the concentration will change very rapidly. Since A is slightly soluble in B, so the concentration of A will change rapidly, and therefore this term, the diffusive term, the diffusion of A in the x direction is going to be significant and cannot be neglected. However, when we talk about the diffusion in Z, the transport of A in the z direction is principally by convection. There would be slight change in concentration as we move in the z direction, but the concentration change is going to be insignificant as compared to the concentration change which you are going to see in the x direction. So concentration change in z direction is going to be small as compared to the concentration change which you are going to see in the x direction. So if that is the case, then this term can be neglected as compared to this term. So the summary of this is that the principal reason for A to get transported in the z direction is by convection, and the way A can get transported in the x direction is by diffusion. And since convection predominates over diffusion in the z direction, therefore the contribution of diffusive species transport in the z direction can safely be neglected in comparison to convection in the z direction or diffusion in the x direction. So if you are comfortable with this, then we can proceed to solve it. We can try to solve it, but it is important to understand what is important in any transport process. So in which direction the convection is important, in which direction the diffusion is important, you will always have to keep that in mind and try to use a sound logic to cancel, if possible, the contribution of a term with respect to or relative to other terms present in the equation. So a simple analysis, picturization, understanding of the transport of the species in the x direction and in the z direction would ensure that we realize in the z direction it is because of flow, the motion in the x direction is because of concentration gradient. Concentration gradient present in the z direction is very small in comparison to the concentration gradient which is present in the x direction. So diffusive transport prevails in the species transport in x direction, and convective transport overshadows any diffusive effect, any diffusive transport of the species in the z direction. So this would result in the compact governing equation which you would have obtained if you have used the shell species balance, but as we have seen, it is going to be complicated. It is much better to start with the species balance equation in the right coordinate system and then cancel the terms from that point on to arrive at the final solution, final governing equation, which would then be equals Vz times del Ca del Z is equal to dAb del square Ca by del x square. So this is going to be my governing equation, but I would like to draw your attention to this to the dependence of the species transport equation on the solution of the momentum transfer equation. So in order to solve the problem, the prerequisite is that you have an idea of the expression of Vz from Navier-Stokes equation, from the solution of Navier-Stokes equation, because you understand in this figure Vz, the velocity in the z direction is going to be a strong function of position on the Vz which is in this direction. So this is your Vz. Vz is going to be 0 due to no slip condition on the wall, and since we have a liquid gas interface at x equals 0, so at x equals 0 the shear stress is going to be 0. So the conditions that were used to obtain the solution of Vz, which is from Navier-Stokes equation. So you write the Navier-Stokes equation, and when you write the Navier-Stokes equation for in the z component, and it is a free flow, so it is only due to gravity, and the boundary conditions that you have used are at x equals L, Vz is equal to 0, and at x equals 0 del Vz by del x is 0, which in other words is saying that tau is going to be equal to 0. So this is no slip condition at the liquid solid interface, this is no shear condition at the liquid gas interface. So, no slip and no shear at the liquid solid and at the liquid vapor interface. So, when you do that, this shows the coupling between the mass transfer, the species transport equation, and the momentum transport equation. Unless you solve the momentum transfer equation in order to obtain an expression for velocity, you won't be able to solve the species balance equation. So, this appearance of velocity in the governing equation of mass transfer couples the mass transport process with the momentum transport process. Okay. So, as I mentioned many times before, there is a one-way coupling between momentum transfer and mass transfer as long as the properties remain constant. So, mu is not going to be a function of position, mu is not going to be a function of concentration, since the gas A is sparingly soluble in B. This ensures that mu is a constant, and therefore, the solution of Navier-Stokes equation is decoupled from the species transport equation, and it can be solved. The Navier-Stokes equation can be solved independently to obtain the expression of velocity in the z direction. Had it not been the case, then both the momentum transport and the species transport equations will have to be solved simultaneously, creating enough complexities, which would probably require solution by numerical techniques only. So, we know what is this Vz going to be. We have an idea that Vz for such a case is going to be equal to Vmax. It is going to be a parabolic distribution, 1 minus x by delta whole square, and this Vmax is the maximum velocity which is there in obviously in at this point. So, the expression for Vmax is provided. I will not go into that once again. So, your final form is going to be Vmax, which is a constant times 1 minus x by delta whole square times del Ca del z equals dAb del square Ca by del x square. Okay. So, this is the governing equation, the final governing equation after you bring in the expression of Vz. So, the boundary conditions which are required in here is that at z equals 0, this was the figure. So, this is the wall, and you have the film of liquid which is falling. So, this is your liquid, and this is x, y and z, the same figure that I have drawn over here. This is delta, this is w, and this is L. Okay. So, at z equals 0, that means at the beginning, at the top, the liquid starts as a pure liquid. So, liquid film begins as pure liquid. So, no A is present in the liquid when it comes to in contact with the wall. So, at z equals 0, that means in this plane the liquid is pure liquid, and as it starts to travel downwards, it is going to absorb A and so on. And then at x equals 0, Ca is equal to Ca0. So, this Ca0 is the interface concentration of A in B, and in many cases it is the solubility of A in B. So, what you get here is that at x equals 0, that means on this plane at x equals 0, for any value of z and of course any value of y, the concentration of A remains constant, which is equal to the interface concentration or the solubility of A in B. At the other end, which is at x equals delta, what we have is then a solid wall. at x equals delta we have the solid wall, so no diffusing A can penetrate this solid wall. So therefore the solid wall will behave as if it's an impermeable wall as far as A is concerned. So we understand this is going to be del Ca by del x to be equal to 0. So these are the three boundary conditions which one must use in order to solve for it. In this form, an analytic solution for this is not possible. So we are going for a limiting solution. So what is a limiting solution? We will assume that we are going to solve this equation for a very short contact time. So what is this implication of a short contact time between the liquid film and the gas? So if you have a short contact time, then if this is the liquid film, then a species A which gets absorbed at the liquid vapor interface, it doesn't have enough time to penetrate deep into the liquid. Before it penetrates deep into the liquid, it reaches L, that is the end of the film, end of the contacting process, and therefore during this contacting process, during the time when A is in contact with B, it cannot penetrate much into the falling film of B. So we understand that what is the velocity profile that's going to be. So the velocity profile would probably look like this velocity profile is definitely a parabolic velocity profile. So it's something like this. So the velocities are going to be this, a parabolic velocity profile. So if this is a parabolic velocity profile, and if this is the A molecule which can only penetrate a little bit into the falling film, so what velocity of the falling film does this diffusing A molecule will sense? If you are the A molecule and you jump into a liquid stream where the velocity is parabolic in nature, where you meet the stream, the velocity has reached its the plateau, the top of the parabola. What you would expect is that for the diffusing A molecule, it is as if the entire film is moving with Vmax. So coming back to this picture once again, if the A molecule cannot penetrate far into the falling film, in that case, for all the A molecules which have gone into the liquid B, it would seem that there is no variation in the velocity of the falling film. It's because of the nature of the velocity profile, and as if the entire film is falling with a constant Vmax, and the variation of V with X to the diffusing molecules, this part is as good as absent. So the diffusing A molecules will not sense that a velocity profile exists in such a case. What it would see is that as if the whole film, the entire film, is coming down with a constant velocity, and that velocity is equal to Vmax. So if that's the case, for a short contact time, when the penetration depth is small, the modified form of the equation would then be that this part would not be present, and it is as if Vz is going to be equal to Vmax. So the modified equation for short contact time, I can write it here itself, is going to be Vmax del Ca del Z is equal to dAB del square Ca by del x square. So this dependence of velocity on x is no longer relevant for the case of short contact time. So I would start with my modified equation again. This modified equation now is Vmax del Ca del Z is equal to dAB del square Ca by del x square. So, at z equals 0, Ca is 0. This was what we have used in the previous case, and now I can use the same, that at z equals 0, Ca is 0, and at x equals 0, Ca is Ca0. I use the same over here, that is at the interface the concentration is going to be equal to some interface concentration, which is the could be the solubility of A in B. And the third condition that I have used is the impermeable wall condition, that is at x equals delta del Ca by del x is equal to 0. But what happens in here in this case is, if this is the falling film, this is the wall, this is the liquid, this is the gas, and the velocity profile is something like this, and we understand that the A molecules can only diffuse only up to a small distance. So, if it only goes into the film up to a short distance, then for the diffusing A molecules, delta, which is the thickness of the film, is as good as situated at an infinite distance. So, the A molecules, since it cannot go far into the film, for the diffusing molecules this delta is at is close to x equals infinity. So, delta is essentially then infinity to the diffusing A molecules. And what is the condition that we should use for x equal to delta? This question is no longer, this equation is no longer valid, it is meaningless, since no A exists at that point. So, we will use the same condition as we have done for boundary layers, and I would simply say that Ca is going to be equal to 0, which is relevant, which is true, because if this is the thickness of the film and A molecules are only very close to this point, because it cannot penetrate much. So, whatever happens over here at a point far from the interface, this is essentially, mathematically speaking, is infinite at an infinite distance as far as the A molecules are concerned. And what is the concentration of A in here? It is 0, nothing. No A exists at that point, since A exists only up to this point. So, in order to have some more mathematical handle on this equation, I would put the condition, I would modify the condition not as the impermeable wall, but that at x tends to infinity, the Ca is equal to 0. So, if you look at this partial differential equation, this is now my IC, and these two are the boundary conditions. So, this is the initial condition, and these are the boundary conditions. Now, if you compare that with the standard solutions which we have obtained for the case of a plate with a liquid on top of it, initially it is 0, but suddenly at t equals 0 it is set with a velocity equal to v, and we are trying to find out how the velocity profile starts to go into the dipper of the liquid as a function of time. In any form of equation with these set of boundary conditions and initial conditions is a prime example of method of combination of variables. This I have done in the case of while solving the problem where a plate is suddenly set into motion, and I am trying to find out velocity as a function of distance, let us say z, and as a function of time, and there we have seen these are going to give rise to an error function solution. I will not do this since I have already done it in the class, but you can once again check how it is done by looking at your textbook, which is Bard, Stewart and Lightfoot. So, the type of situations which would give you an error function solutions are when a plate set in motion. The second could be when you have, let us say, this is a solid object, temperature is initially uniform, at time t equal to 0, one of the boundary temperature is changed to a new value. So, it was Ti to begin with, and suddenly it has been changed to T0, and how would the temperature front penetrate in here? You will get the same type of boundary, same type of governing equation, same type of initial condition, same type of boundary conditions, and the solution would simply be an error function. So, this error function solution is quite common in many fields of transport phenomena. If you get the equation in this form, you can directly write, if your initial condition and boundary conditions are like this, one is at z equals 0, one is at x equals 0 and x equals infinity. If these are the forms, then the dimensionless concentration can be written in the form of error functions, and you can simply cite any one of these two which is solved in detail in Bode-Stewart-Lightfoot, and you can check how you are going to get this, which I will not use anymore. So, once so this is a limiting solution that you get for the case of concentration distribution. In the next part of the class, I would show you how to use this limiting solution to obtain the total amount of mass transfer from the gas to the film, and what are the parameters on which it would depend on.